Hello everyone. Thank you for joining us for today's CellSage webinar. It is a little bit past 10 o'clock, so we'll go ahead and get started. My name is Wyatt Pena and I'm a project manager at Ridgetop Group. CellSage is a modeling tool for diagnostic and predictive evaluations of battery life and mission readiness. This innovative technology was originally developed by the Department of Energy's Idaho National Laboratory and has been licensed and enhanced by Ridgetop Group. Today's presentation will be covered by myself and Dr. Kevin Gearing from INL. Kevin is a distinguished scientist at INL and has received several awards for his research contributions and technology developments such as CellSage and his Advanced Electrolyte Model, AEM. In 2014, Kevin received an R&D 100 award for AEM, and around the same time frame, he was also working on CellSage. We are very fortunate to have Kevin's expertise, and we are happy to have him join us for this very special product introduction today. For today's agenda, we'll first start off by talking a little bit about Ridgetop Group and INL. Then we'll cover the CellSage introduction and overview. And then Kevin will talk a little bit about the development history and the underlying methodology. And then we'll look at the technology enhancements and commercialization with Ridgetop Group. And then we'll move into the future developments and opportunities section. And at the end, we'll summarize and have time for questions. So a little bit about Ridgetop Group and INL. Ridgetop is located in Tucson, Arizona, and we were incorporated in the year 2000 and have been servicing the aerospace, automotive, and industrial and government industries. We are an AS9100D certified and ISO compliant facility. The products and services that we specialize in are in the test and measurement sector, engineering design services, and system level solutions for PHM, IBHM, and CBM applications. INL is located in Idaho Falls, Idaho, and INL is a part of the U.S. Department of Energy's complex of national laboratories. INL performs work in each of the strategic goal areas for the Department of Energy, and that is energy, national security, science, and the environment. INL is the nation's leading center for nuclear energy research and development. Next, we have a short video that's also on YouTube, and that'll be summarized in the next slide.
So a brief recap of that. So CellSage is an advanced battery and cell aging software simulation tool, and it represents over a decade of research in electrochemistry, physics, and thermodynamics. CellSage can assess how various battery chemistries age and degrade in response to different usage profiles during a simulated battery life cycle. This leading-edge simulation platform allows battery end users to create what-if scenarios to weigh the impact of operational and environmental stress factors on battery performance and battery health. The simulation results and analysis provided by CellSage will help select the most appropriate battery for a given measurement. CellSage is comprised of three particular modules. The CPC module, which is for capacity, power, conductance behavior. 2 is the kinetics module for voltage drops over arbitrary conditions. And the TA module, which is a fairly new particular module that has been developed by INL and Kevin, is for materials-driven transient analyses. The full YouTube video can be accessed in this link, and as a general note, the slide deck will be distributed to all registered attendees. So the CellSage value proposition, there are some brief bullets here that we can talk about, is that CellSage can decrease lifetime testing by at least 50%, can reduce cost of battery packs by at least 5 to 20%, and refine battery management strategies to reduce battery aging by at least 10 to 25%. There is a rich data output set for battery health diagnostics, and CellSage is covered by 4 U.S. patents. Ridgetop Group is INL's industrial and commercialization partner for this technology. Next, we'll move into some of the CellSage development history and methodology as presented by Kevin.
Thanks, Wyatt. So we're going to go back at least a decade. In the time frame of 2007-2008 is when we submitted the copyrights for the CellSage CPC module and the kinetics module. Following that, and between 2013 and 2017, 4 patents were issued by the USPTO covering the different CellSage capabilities. And within the middle of that, Ridgetop Group started their licensing of that technology. Following that, Ridgetop and INL developed the first graphical user interface version to commercialize this product. This was refined in 2019, and also during that time, INL submitted a patent pending covering the aging simulation of complex battery charging protocols. The reason why that's important is there's been an emphasis in recent years in accelerating the charging process for lithium-ion batteries to achieve a fast charge. And so there's, with that comes a lot of complication on the aging side. And so we saw an opportunity to go ahead and submit some IP on that topic. This year, Ridgetop and INL have released and created an installation base with CellSage CPC simulation module, and also submitted another patent pending item covering battery aging determination from a transient analysis framework. Okay, next slide. Let's just kind of go over some basics here regarding the need and solution. Battery energy storage in general carries with it a lot of uncertainty on how well the batteries will survive in different dynamic conditions in actual field use. So depending on the application, these conditions can change markedly over the timeline. Also, industry needs accurate determination of what I would call operational envelopes of batteries as they age and as conditions change. So an operational envelope would cover a lot of different regimes that impact what the battery experiences. Regimes like temperature, current, voltage, other stress factors that we could name that have a profound influence on aging mechanisms. Battery use over multiple domains can be quite complex due to the coinciding stress factors that can emerge depending on the use conditions. So duty cycles, environmental factors, and disparate aging among cells in a string or a pack can all complicate how we look at battery aging. So the solution that we're providing through CellSage, this software targets the battery life cycle diagnostics and predictions, as well as exploration of life-prolonging conditions. CellSage is also adaptable to application-specific analysis of battery life cycle trends. And this helps to support project planning, reduction of investment risk, and ongoing system monitoring to control and maximize battery life. So those of you who are kind of keeping track of where battery trends and battery demands are going, especially through our Department of Energy, will realize that the new demands placed on batteries create new aging effects that are difficult to foresee. In recent years, there's been a push through DOE and also private industry, like the big corporations, Samsung and Toyota and such, to look at higher voltage operation, lower temperature conditions, and faster charging. So these are examples of conditions that put much higher stress on battery materials. CellSage connects the battery material response to these types of stress factors, and we are trying to keep in step with what is anticipated for battery use, and we're trying to constantly keep CellSage fresh and relevant for what's going on in the battery space. Okay, next. This just kind of reiterates what we've already seen in some of the previous slides, but one thing I would point out here is the important triad between capacity, power, and the charge transfer kinetics. Between these three, we have a very good thumbprint for what is happening in battery health and battery aging. Some of the key parameters, the input parameters that we provide through CellSage are some of the things you might expect. So this would be temperature, state of charge, or voltage, and also the range of voltage for when we do power calculations, cycling regime, whether it's a calendar or cycle life type condition, the cycling magnitude and the frequency. There's also some algorithms that deal with daily thermal cycling and its impact on the stress factors that impact battery aging. Also, we have allowance for placing a given battery in a different geographical location if the battery use carries with it some environmental factors like temperature, exposure. So there's a library of over 130 cities within the US that reside within CellSage, and you can pick any one of those or all of them if you wish and do some simulations. And also cell chemistry is an important input. Okay, next. Kind of the bottom line foundational thing that we want to know through CellSage is we seek to understand how batteries will age in their intended application. So this is a big challenge because the intended application out there varies with whoever's might be asking the question. There could be millions of different modifications on how a battery is used. And so depending on that use, it has a profound impact on the ultimate aging profile. So the central issue is, can a chosen battery meet the performance demands for an application under a wide range of factors? And those factors can change daily or hourly or monthly, seasonally. And what is the durability of the battery under those types of conditions? So what I've drawn down here at the bottom of this slide is what I call usable power envelopes. And these are drawn over multiple domains of interest. I mentioned temperature, current, voltage, and things of that sort can represent the different domains. A new cell or a new battery pack would be represented by the green, the darker green contour. As we go along the aging timeline, that contour, that envelope can start to shrink. And it can shrink in different ways. It can shrink more, say, for temperature, in the temperature domain, and causing it to deform its shape over time. And this has a profound effect on what can be achieved with that battery as it ages. Now, granted, there's not a lot of knowledge out in general about how these power envelopes actually change over time. And so this is not only a challenge, but it's an opportunity for CellSage to be placed in this area of interest, because it does impact how battery deployment will proceed throughout the US and the world in different areas. Okay, next. Kind of keeping with this theme of power envelopes, this is a simple example of what we might see for plotting power versus the power pulse time. And in this case, we've plotted isothermal contours. So if you go up in the top left plot and go at the top red curve, that's the higher temperature. As you go down in temperature, your achievable power starts to drop. So this is seen in a lot of battery chemistry. This is really nothing new, but this is just kind of rendered here to show what we might anticipate as a battery ages for the required power envelope, which is given in the shaded green, versus the achievable power in the dashed blue contour. So as we go to battery aging and we go to the right, we see that this dashed blue contour starts to shift and shrink. And as we go to the bottom, at more advanced aging, the power envelope is starting to be outside and not aligning with the required power envelope. So based on that, you could see areas of pulse time and also temperature that you can no longer operate within. So being able to predict how this would play out in a battery chemistry for an intended application is a very important aspect of where CellSage can help predict these changes. Okay, next. Okay, another key aspect of battery aging is what we call path dependence. Path dependence asserts that it is the sequence of aging conditions along the timeline, as well as their magnitude, that has a direct influence on the irreversible aging trends of battery systems. So if you were to take this curve in the bottom here, where we have 4 conditions, I plotted 4 conditions just out of convenience, but we could have 4, 40, 4,000, whatever. We have a large number of different distinct aging conditions over the timeline. And if you were to randomly place those and test the battery under different random assortments, you wouldn't necessarily always end up at the end of that fourth condition where it touches that dashed red line. In other words, the aging outcome will depend on the sequence, and the aging outcome can be above or below that red dashed line over time. So that's aging path dependence. It's a complicated outcome of thermodynamics and the fact that a battery cell is a closed system except for heat and current. And because of that, it has certain thermodynamic outcomes that must obey that and relate back to the conditions in the history of the aging up to the point where a new condition is encountered. Okay, next. Some of the aging parameters or stress factors that we look at in many ways are covered here. Temperature, state of charge, the delta state of charge, which can happen over a given pulse duration, calendar life versus cycle life, pulse magnitude, and pulse mode, whether it's constant current, power, or voltage. When it comes to charging, we look at similar things, but we're very much aware that elevated cutoff voltage or voltage max is a very important thing to be aware of, because a lot of battery aging can be encountered by operating and maintaining a cell at a high state of charge. Other things we could look at and add to the modeling would be pressure effects, mechanical shock, and thermal cycling. Okay, next. Okay, so thanks for your patience as we kind of went through some introductory on CellSage and what it is, what it does, and what the foundation is. Now we look at a little more of utilizing it to describe capacity loss in lithium-ion cells. When we talk of capacity in a lithium-ion system, there's two main categories that we track and we quantify, and we can actually break these down into different contributions as well. One is the fraction of active and available sites. Some refer to this as active material within the electrodes. So this is the host material on cathode and anode sides. The other category is the fraction of available lithium, and some would call this lithium inventory. So you need both categories within a cell to keep it healthy. If you become imbalanced and have too much active material but not enough lithium inventory, or vice versa, then you can start to see a drop in cell performance. Each of these have their own unique pathways for becoming degraded and being lost over time, and that's in this lower set of boxes here I won't go into. Okay, next. Here it shows some of the underpinning mathematical basis of CellSage. We use a deviation from baseline approach that allows us to do an initial thumbprint of a cell chemistry to a baseline test condition. So based on what that test condition is, gives us some good early information on how the battery responds to, say, temperature and cycling rate and duty cycles and duty cycle frequency, things like that. And that can serve as a baseline, which is important for two reasons. It gives us that initial thumbprint, but it also gives us some really good early diagnostics on what is happening with lithium inventory and active material. Now, as we change and go to an arbitrary off-matrix condition that's outside the testing, we assign the algorithms within the CellSage assign these deviation from the baseline in each of the stress factors. So we go to the first order terms, as you see in this top red box, and we can also add secondary and third order terms as might be needed according to what we determine for the cell chemistry. By the way, the term psi, for you Greek-loving mathematicians, the psi here represents a performance metric such as cell capacity loss. Okay, next. Okay, finally we see some results. These are very simple results for our testing for Department of Energy using a nickel, cobalt, aluminum cathode or NCA cathode with a graphitic anode. And these were tested in different ways, and in some cases tested over 2 years. And along the way, we tracked the capacity fade under different conditions. So what you see here, the symbols are the test data, and the blue lines are the CellSage results. Now, what you see here is the overall capacity fade for the cells. Within that is also the breakdown of loss of lithium inventory and loss of active material. So you're just kind of seeing the overall result here without it being too confused with adding this differentiation of the other mechanisms. We can look at a low rate capacity loss type of scenario, like a C over 24, where it takes 24 hours to discharge the cell, and generally that's is minus any kind of polarization effect. And we also track something like this 1C rate, where the full capacity is discharged over 1 hour. Now that will have some aspect of polarization in it, and the model also provides details on quantifying that effect versus the irreversible loss effect. So next slide. And here's an example where we can look at reversible and irreversible components to cell aging. This has a lot of information in it, and I'm sorry that it has so many curves that I won't be speaking of individually. But the long story short is that we can use the model and its framework to detail the irreversible capacity loss. Now that's the permanent loss of capacity, both in terms of lithium inventory and active material, and also extract out the reversible loss that's due simply to the polarization effect of going to a quicker rate. So this is quite important, as it turns out, because as you operate your chemistry, your battery chemistry, you really need to be aware of what is the context of when you say capacity loss. What that always needs to be spoken of with respect to a rate of operation. So in order to help standardize that, we provide this tool that adds the ability to determine reversible versus irreversible loss within the battery. Okay, next. Another thing that the model does for the sake of diagnostics is look at the actual molar concentrations of lithium content and active sites within the electrochemical cell. And so this is important for those who might be designing new electrodes or designing a cell and trying to balance cathode and anode and so forth, and to see how these might be changing over time and causing an imbalance in the cell. So earlier I said it's important to have good, healthy lithium inventory as well as active material inventory, and to keep that in balance as the cell ages. And so by looking at these types of curves, we can see where the imbalance might start to occur and become highly problematic. And these are just some other battery chemistries. The one on the left is basically, I believe that's an LTO LFP cell. And on the one on the right is LFP type cell from A123. So that'd be a 26650 type of cylindrical cell that A123 has put out some white papers and brochures to describe. The funny thing is for the same cell, they put out information that shows different performance. So you can pick which one you like the best, or you can use an average to try and estimate what that particular LFP chemistry might be doing over extended time. The symbols in each of the sets of curves are the actual data provided by the vendor, and then the solid lines are the CellSage outcomes. Okay, next, please. By far, temperature is the most important stress factor that we see in a lot of applications. as long as we provide reasonable bounds on state of charge. Temperature is something that is manifest in different ways. We can talk about ambient temperature, if the cell is exposed to some extent to the ambient environment. Also, the ohmic heating of cells can produce temperature hotspots, and if temperature management, the thermal management is not adequate, that heating can become quite profound. We could have local hotspots in battery packs due simply to the configuration of the strings, and if the thermal load is excessive for the thermal management, then these hotspots can cause local aging that's greater than the colder spots. And also thermal cycling, where we might have a daily thermal cycle that starts at a cold condition and goes up to a warmed condition. That can happen once or more a day, depending on the type of vehicle, say in an automotive application. So those are the things we are aware of, and by and large, how CellSage is configured, we provide ways to look at local hotspots, daily thermal cycling, and the ambient temperature effects. Okay, next. So next couple slides are going to show an example of why it's important to consider the geographic region in which a battery might be operated, and also the importance of thermal management. Here we have roughly a dozen or more cities within the US and their annual temperature profiles month to month. We see some extremes here. If you look at the green squares with the green curve, this is Duluth, Minnesota. We see that on the low temperature side, it's quite sobering. No place to vacation in the winter unless you're an Alaskan, perhaps. And then we can look at Phoenix, the diamond symbols in gold, where the summertime can be quite damaging to batteries if there's no aspect of thermal management to prevent that. So, like I said earlier, CellSage has 130 cities within the US that have these types of temperature profiles embedded within the code, and so we can do simulations with the temperature profiles, and also with or without thermal management, to see how we might be able to place a product across the US and maintain some autonomy of cell longevity, weighing out the thermal management that we might need to impose upon that product. Okay, next. So this type of simulation was done using the 130 cities across the US, and we also used some grid triangulation to interpolate between the cities, so we could have a nice overlay of the response across the entire 48 states. On A, the top box A is battery aging of a NCA graphite lithium-ion chemistry using a 10-year simulation. And the box of aging that's toward the right, the colored, the rainbow colored, goes from around, I believe, 40% to around 55 or 60%. So most of the US is falling within that range by the end of the 10-year mark, but we see some extremes. We see that as we go to Death Valley and parts of Arizona, and that whole region in the southwest, there's quite severe aging there, as well as southern Texas and southern Florida. We also see that as we go to the places with higher elevations, the mountainous regions, Rocky Mountain West and Appalachian regions, we have much less aging because of the cooler climate there. Also, Pacific Northwest, Seattle, and so forth seems to be kinder to batteries than the hotter climes. So as we go to panel B, this is where thermal management has been imposed. And if I remember correctly, we set our maximum allowable temperature at 35 degrees and the minimum at around 10 degrees. So when we do that, we see a much more well-behaved and more consistent aging across the U.S. compared to the case with no thermal management. This can be done for other battery types, and this would be, again, if you're looking to place a product that has some aspect of exposure to the geographic temperature type of environment, then this is an important outcome. Okay, next please. So I picked a few examples, basically we just saw, but using an LFP cell chemistry, excuse me, and looked again at this aspect of no thermal management on the left versus with thermal management on the right. The cities we look at here are Phoenix, Denver, Miami, Honolulu, New York City, and Seattle. So as we operate this LFP 26650 type of cell, we assume a C/2 cycling basis and a 90% state of charge as the nominal state of charge that's used to initiate battery operation. You see that Phoenix is obviously a recognizable case of having a higher battery aging because of the hotter temperatures. And if you'll see its profile, you notice the stair stepping. That's simply due to the annual temperature profile and how the battery ages more in the summer months than the, say, winter months and leading up to that in late fall and early spring. So that stair step is something that's realistic and anticipated for the different scenarios here. Seattle is a very nice city when it comes to battery longevity because it has mild climate, not too hot, not too cold, and it's as if it's like it preserves batteries. So maybe good for people in Seattle who own hybrid and electric vehicles. As we add thermal management and impose a Tmax of 30 degrees and Tmin of 10, we see that these curves start to fall and they start to collapse into a more narrow region of capacity loss. So this is a very good way to say we can have something in Phoenix that's using a battery achieve the longevity of something that's more in line with Miami and Honolulu and last just as long there. So I think there's a little bit more on the next slide where I have, oh, this is SOC, okay. I'll just touch on this briefly. State of charge is another parameter that's looked at for aspects of battery performance and power delivery. Obviously, if you're at a higher voltage, then you're going to be having higher power output from your device. But there's a trade-off because as you operate at higher SOC, that initiates more of a response to the stress from the electrochemical cell, and you have more degradation at the higher SOC. The context here was, what if we operate the battery like a lithium-ion cell at higher SOC in the wintertime, but then drop that down in the summertime? Because in the wintertime, we all know that the batteries, lithium-ion batteries, do much more poorly at cold temperatures than they do at warm temperatures. So this is to kind of help compensate for the loss of power by boosting up the voltage. And that little box that's inset, if you go through that over the 12-month period, that annual average SOC is 80%. So we compare that case against just keeping a constant 80% state of charge throughout the year. And so if we would compare, for example, the red curve, which is the SOC constant at 80%, having a Tmax of 40 degrees with thermal management, and then we compare that against the black curve, which is having SOC as a function of time, as in the inset, with Tmax of 40 degrees, we get these discharge capacity loss curves that are roughly 12 to 15% different by the end of the 250-week period. And this is for a Denver, Colorado case. So again, higher SOC, it's a short-term gain in power management, but you end up losing life of the battery because you're introducing more stress. Okay, next, please. We can also be looking at strings. The code allows for up to 25 cells in a series string. It's not constrained to that. It's just kind of what we picked as a reasonable upper number. And then impose some kind of hotspot. We can define what the hotspot looks like, its magnitude, and we can also define the temperature profile, whether it's a linear or parabolic or hyperbolic type of profile. So the question is, what does it mean, and what's the consequences if we have a hotspot in the middle of a string like this? So let's go to the next slide. In this case, we have a 7-cell series string. The middle string, number 4, has a hotspot of plus 10 degrees. And then the cells on the edge have a 0-degree hotspot, or they're just at the 30-degree mark. And then we operate the code, and then we track how the cells age according to the hotspot. At 50 weeks, 100 weeks, 200 weeks, we see this growing capacity loss in the middle of the string, to where at the end of the 200 weeks, the comparison between the middle and the edge results in almost 15% extra capacity loss. Now that's important in 2 ways. It's not only capacity loss, but it's also impedance increase. Generally, the two happen at the same time and for the same reasons. Capacity loss and impedance can have similar root mechanisms. So that automatically tells us that this string is going to be having some considerable power delivery issues as we start to age it under this hotspot. Okay, next. I think I'll skip this one for sake of time. This just tells us how we are calculating power. And I think I'll skip this one because the next one has a little more information. Okay, so based on what we just saw with hotspots and string type calculations, I've compared that same list of cities, the 6 cities given at the top right here, looking at power loss estimates. In this case, I used an 11-cell string with a hotspot in the middle. Again, it's plus 10 degrees. And there's 2 types of power pulses that I look at. If you look at the solid curves, these represent shallow power pulses where the SOC is within a fairly narrow window. And so it'd be maybe ranging between, say, 80 to 90% SOC. The dash curves represent deeper power losses that cover a much broader range of SOC, something like maybe 90 to 30%. And all that can be defined in the model. You're allowed to put in the Vmin and Vmax of the power calculations, and it takes that information directly. So what we see on the left panel is the power loss under no battery thermal management. We see that operating at the shallow power pulses results in less battery aging than if we go to deeper power pulses. And that intuitively, that makes sense. Phoenix by far is the worst case by going down to below 50 watts after it started out around 215 after the 10-year simulation. And to the right, we have the same set of curves, but with battery thermal management. Same conditions as we saw before, but these are arbitrary to the user. You can input whatever you like. Tmax at 30, Tmin at 10 degrees. And we see that as we use thermal management, the curves go up, so less power loss. And again, they start to collapse and become within a more narrow range for each set of pulse condition, whether it's a deep pulse or a shallow pulse. Okay, next please. And I think this is one of my last technical slides. This covers what we call the kinetics modeling, or the kinetics of the charge transfer reaction. And this is important for lithium-ion systems, because what we often need to know is how much voltage drop do we encounter when we pick a particular state of charge, current, and temperature to operate at. How long can we sustain a particular power level at those conditions before we hit a voltage limit? So this is a very important contribution toward designing and selecting a lithium-ion cell that will be intended for a particular application. There's some, for example, there's some aeronautic type of applications we could list, where there might be cooling of batteries as a something like an air taxi or other device goes up and gains elevation. As it gains elevation and the batteries are cooled, are they going to be able to still produce the power delivery that we had hoped? So the kinetics module allows some pre-screening and some evaluations of what is possible with a particular electrochemical cell. Okay, thanks, Wyatt. I believe that's the end of my section.
Yes, so thank you very much, Kevin. We do appreciate that. And yeah, you gave us some good insights on the CellSage development history, as well as the underlying methodologies being used to capture the modeling tool. So
Okay.
next, we'll take a look at the technology enhancements and the commercialization process with Ridgetop Group, and I will jump straight into that. So the Ridgetop Group graphical user interface that Kevin talked about that we've been working on is an easy-to-use GUI system that was developed by taking the legacy command line interface and packaging that functionality into a modern GUI. So the Ridgetop CPC simulation module utilizes a flexible system architecture that is interactive and streamlines the data plotting process and analyzing data features of interest. These enhancements have been designed and implemented by Ridgetop and allow for a more intuitive end-user experience. The software application is offered through evaluation trials and annual license agreement. And to the right, you can see an example of the most recent GUI revision, and this is a product that we've been working with a lot of our customers to work on. So some of the typical input parameters that Kevin talked about throughout the methodology section are obviously your cell chemistry, your simulation time, your state of charge, your relative cycling severity, the temperature mode, as well as those annual temperature profiles related to over those 130 U.S. cities, the thermal management conditions, the effects of daily thermal cycling, and also the string analysis. So it is important to note that Ridgetop and INL can provide customized simulation models for particular applications and chemistries via software services. So some of the data outputs that are produced by CellSage are definitely related to the string analysis, the path dependence as those aging parameters such as temperature, state of charge, cycling or dream over time, and the effects of DTC, which is dependent on the geographic location, are all relevant to producing good diagnostics and outputs from within the tool. There is also a CellSage diagnostics data output file, which provides the intermediate simulation results determined by the regression models embedded within the software. This file is designed for inspection and validation of each simulation. So we do have a brief example simulation being run here, and I might skip over some of the sections for the sake of time. But here we're effectively opening the application, requesting the license, entering the password. Okay, and now we'll select our chemistries. Right now we have 5 available chemistries. You can see the reference conditions, your simulation time, your state of charge that you'll be selecting, and then your relative cycling severity. So for this example, we'll leave that at about 1, and then we'll keep stepping through. So you have your next and your previous button, your ability to add your cities and those temperature profiles, and then as well as the other thermal management conditions. So we'll jump through this again to speed up some time. We're now at the string analysis file, adding 9 particular cells in this string, the current through that string, the magnitude of the hotspot, your thermal management upper limit, and then your max cell starting voltage and your minimum cell stopping voltage. So once you do that, you're able to select your data output directory. For here, I'll use the default. I'll run the simulation, and you can see this 2-year simulation is done in a mere matter of seconds. So there it is. It's complete. Now you can exit the application, or you can inspect those data output files. Again, for the sake of time, I'm kind of speeding this up here, but you can see those the CellSage diagnostics, the path dependence, and the string analysis file. And we also offer a parameters.txt file, which will tell you all of the data inputs for a given simulation. And all of this information is stored nicely in a simulation folder that's time-stamped. Here is an example of looking at the Fairbanks, Alaska data and generating a plot. So Excel is an easy tool to kind of demonstrate this in, but obviously other tools like MATLAB can offer much better plots and analysis. So this was a visual of each of those plots. So we added Fairbanks, Idaho Falls, where Kevin is at, and Phoenix. You know, we've been talking a lot about Phoenix, and the historic data is very much relevant to the temperatures we're experiencing in Arizona today. You know, it's been a very hot summer with very little rain, and I can imagine a lot of the battery systems that are out there are experiencing these aging effects. But to put things in a little bit perspective, I ran that simulation with and without thermal management, and you can see without thermal management, Phoenix at the end of that 2-year simulation period almost doubled the amount of capacity loss. So that starting initial capacity was at 2100 milliamp hours for that particular cell, and it dropped by approximately half of that percentage. And the same is true, the relative trend, where if you have a thermal management system in place, your results of capacity loss is not as much as a system without thermal management. So some of the CellSage key benefits as we kind of near the summary section here is that CellSage performs diagnostics to enable mechanistic evaluation of the degradation process. CellSage predicts battery life under arbitrary simulation conditions for warranty validation and supports optimization of battery pack design and related thermal management systems for lighter and more economic designs. Oftentimes, battery systems are over-engineered, or they may or may not have a thermal management system. So CellSage allows you to investigate the performance optimization that you can gain by looking at a thermal management system. CellSage extends battery life and improves safety when integrated with onboard thermal management and monitoring frameworks. It supports evaluation of disparate aging within cell strings and can be applied to any device or system that undergoes gradual aging processes, such as those related to biological, geological, morphological, electronic, and mechanical systems. So some of the future developments and opportunities that we'll be talking about, Kevin will cover these next 2 particular slides, but effectively there's 3 modules within the CellSage family. So today we focus on the CPC module, so there's also the kinetics module and the TAA module.
Yeah, thanks, Wyatt. Simply, the 3 modules provide a very comprehensive view of battery aging mechanisms, starting from the materials level, where the TAA/SP module resides, and it can communicate with the CPC and kinetics modules to provide a balanced view from molecular to macro scale. That's what this is intended to be. Okay, next. Here's an example of where we use the TAA module to look at fast charge conditions for a NMC 532 cathode that is paired with a graphitic anode. It's a 1506T from Superior Graphite, where this particular set of electrodes is 70 micron thick each, and it's intended for a 10-minute charge protocol. So we were investigating what happens as we start to increase the charge rate from a 4C CC/CV. So it means we start with a constant charge, we reach Vmax, and then we switch to a constant voltage. And we see quite a profound aging difference. And this reflects very closely what is actually in the data. As we go to 4C, then we investigate some multi-step type of protocols, and then we go to a 6C rate. The TAA transient analysis predicts very closely what is happening at the electrodes for loss of lithium inventory. Okay, that's all I had on that one.
Okay.
Thanks.
Thank you again, Kevin. So yeah, if we look at the Ridgetop and INL relationship for commercialization, INL again was the original technology developer by way of Kevin, and selected Ridgetop for this commercialization process. Through this process, we've been focusing on battery end users and battery manufacturers as our main customer segments. We're also leveraging our relationships with the different government agencies, such as the Department of Energy, the DoD, and NASA. So there, again, some of the value props are reducing your warranty cases, reducing battery aging, and optimizing battery pack design and performance. So some of the target customer segments, if you take a little deeper dive, we have existing relationships in the robotics industry, the electric vehicle manufacturers and supplier industry, and then also grid energy storage, power tools, and universities, researchers, and government agencies. Some of the future target application areas that we're looking at are with laptop manufacturers, battery manufacturers, and the unmanned aerial systems and UAVs. So down in the bottom here, we have our technology pipeline. You can see in Q4 this year, we're currently working on and planning to release an upgraded CellSage CPC module with built-in plotting and analysis. The existing CellSage CPC simulation module is ready for distribution, and you can contact a Ridgetop Group sales representative to help you out with that. In Q2 of next year, we'll be releasing those CellSage Kinetics and CellSage TA modules. And in Q3 to Q4 2022, we'll be building that cell chemistry library, implementing global temperature profiles, and embedding diagnostics in monitoring in a larger battery management system. So some of the other possible applications are the lifetime and fate analysis for materials and material-centric devices, multi-component large infrastructure items, geological processes, and then focuses to connect those mechanisms to aging, detect and predict where critical thresholds are approached over time, and optimizing conditions of use to prolong device life. So in summary, the immediate benefit of CellSage is to provide a basis for diagnosing and predicting battery performance and aging over arbitrary conditions, thereby improving battery design, performance, and management. Knowledge of aging path dependence gives insights and to optimize usage conditions, to prolong the lifetime of batteries in service, and to predict that if warranties are met. Battery aging trends in vehicles and grid applications will vary over a diverse usage conditions, where foremost parameters are geographic locations, load patterns, and frequency, and to the extent of thermal management. So this capability enables improvements in cell materials, string dynamics, and management schemes. Model parameters are physically linked to cell materials and design and are chemistry specific. So we do thank everybody for participating in today's webinar. We did run a little bit over the original hour that we had scheduled. So if there are any questions at any time, feel free to email us. And as a general reminder, these slides will be distributed to all registered attendees, and I can cover some of the next slides as well. We do have some additional webinars coming up as they relate to other Ridgetop product lines for Sentinel IT and Sentinel Interconnect. So those will be coming out, and keep an eye out from an email from one of our Ridgetop Group representatives. So thank you, Kevin, for joining us today. We do appreciate it, and I think we covered a lot of great material, and I hope everybody enjoyed it.
Thank you, Wyatt.
Okay. All right. Thank you, everybody. Have a good day.
Bye-bye.